Okay, good afternoon, everyone. I'm Andy Cohen, the director of the IAS. It has been a tradition for a number of years now for the IAS to host lectures explaining the science behind the Nobel Prizes, and this year is no exception. Today's lecture is the Nobel Prize in Physics, and we are especially pleased that our own IAS professor, George Smoot, will be delivering today's lecture on the discovery of gravitational waves. George, who has been a frequent visitor to HKUST before being appointed as an IAS professor, is quite a distinguished cosmologist. He obtained his undergraduate and graduate degrees at MIT and subsequently moved for the sunnier climate of California, where he has spent the bulk of his professional career. George is an observational cosmologist and is responsible for a variety of important results in physics and cosmology. Most notably, he is a co-discoverer of the precise black-body nature of the cosmic microwave background and the small fluctuations that are associated with the formation of structures in the early universe, a discovery for which George shared the Nobel Prize in 2006. Today, he's going to tell us about the discovery of gravitational waves and their importance in opening a new window in the universe. So please join me in welcoming George.
This is a talk which is about the Nobel Prize, but if you were paying attention, this has been a big story for the last almost 2 years. And just in this fall, there were 3 major news stories, and I'm going to spend some time talking about them. There was an announcement 2 weeks before the Nobel Prize of another observation, which I'll talk to you about. There was the announcement of the Nobel Prize on October 3rd, and then a couple of weeks later, there was an announcement of the first detection of 2 neutron stars coalescing. And so we'll talk about this. I've known for a while it's going to be. So with 2 colleagues from Mexico, Jorge and Salvador, we wrote a brief history of gravitational waves, which is a good reference, but it's getting out of date because you'll see the field is moving forward very fast. So I was in Mexico for the Day of the Dead and for Dark Matter Day, because we were doing a premiering in Spanish planetarium show on dark matter, and so we did it on Dark Matter Day, and I met with them, and we agreed we would do an update, and so in principle they have a copy of my talk, although we haven't been able to find out how to show it to them online, so I'm hoping this will be online, plus my notes, and we'll do an update to this article. We were very pleased with it because not only did it get a lot of attention, but in fact it became the cover story for the magazine. So that's a reference for some of the history if you want to know more. I have to move along because I have a lot of material to cover, because I started writing this talk as the discoveries were being made, and there's been a lot of things that have gotten released. So the big news on October 3rd was that these 3 gentlemen were awarded the Nobel Prize: Ray Weiss, Barry Barish, Kip Thorne. You probably heard of at least one of them before if you saw Interstellar, because he's responsible for some of the beautiful black hole graphics and that. But they gave it for decisive contribution to the LIGO detector and the observational gravitational waves. And it's complicated, and you'll see more than 1,000 people worked on this. So this is one of the issues about the Nobel Prize, is who you give it to and how do you give the credit to the collaboration. Okay, so let's get right into it. So on the 11th of February 2016, so almost 2 years ago, the executive director of the LIGO's Advanced LIGO Science Team, David Rees, made the announcement at the big press conference and presentations they made that they had discovered gravitational waves, and they'd done it using 2 detectors. Let's see if I can use the pointer. One in Livingston, Louisiana, and this L shape here, and one in Hanford, Washington, with this L shape here. And they saw these waveforms, the Hanford data, the Washington data, the Livingston data, and the 2 data time shifted because of the light travel time is about 1/100th of a second, shifted and inverted because of the angles at which things are going on, to see that they line up, plus these curves in here, which are the numerical relativity plus filtering of the data, estimate of what the signal should look like. So this doesn't look very impressive. And in some ways, it's very unimpressive, except for the fact that it ends a 100-year journey on which there was the prediction that there would be gravitational waves, and a 60-year journey and the effort to try and detect them, and 40 years for LIGO itself. So here's the simulation. There are two large black holes, solar mass black holes. We'll see these are roughly 30 solar mass black holes orbiting each other. And when they do, they disturb the fabric of space-time until they coalesce and they ring down and the signal goes out. The signal goes out across the universe, expanding as a sphere, slightly distorting space-time as it goes along, till eventually it passes by the Earth. So here's the Earth, and it's going to make the Earth expand and contract a little bit. So this is highly exaggerated version of the Earth, right? Expanding, contracting. And every one of you lived through this, right? You were expanded and contracted too. So it's personal. So here's the Hanford part of LIGO. And we'll talk about this for the 36 solar mass black hole and a 29 solar mass black hole that made a 62 solar mass black hole and gave out 3 solar masses of energy and gravity waves. Okay, so let's talk about the details. In the early phases, the two black holes are orbiting as a binary pair, just like the Earth's going around the sun. But because they're so massive, they're radiating away energy in gravitational waves, and as they lose energy, they orbit closer and closer. That means the orbiting speed picks up, right? As you know, Mercury orbits faster than the Earth does, and so forth. The closer you get to the sun, to the heaviest mass or the center of mass, the faster you orbit. So the orbit towards the end will begin to speed up. It speeds up quite a lot just before the black holes touch. The black holes' event horizons, their parent horizons first, and then their event horizons touch, and they merge into a single black hole. It's kind of elliptical shape, and it has to oscillate to become spherical shape, give away some energy. So that's the whole aspect of what you're seeing in this kind of an event. And what you'll see is this all happens very quickly. And so this was just a picture that I put out at the slide at the time. This is just at the time there was a Brexit vote. And this shows you the scale of the orbits when these guys came in the viewing, right? And so they eventually coalesce. All right, so let me go through the details. The source distance we know to be 1.3 billion light years. That is, this event happened 1.3 billion years ago, and it took that long for the gravity wave to expand out to see the Earth. And the one black hole was roughly 36 solar masses. The other one was almost 30 solar masses. And when they merged, they made a 62 solar mass black hole, and they put out 3 plus or minus a half, because in science you have to have error estimates and so forth, in gravity waves. This is an amazing amount of gravity waves. It's 50 times brighter than all the stars in the visible universe during that fraction of a second when it was going. So this is an extremely powerful event. So in physics, energy divided by time is power. So this is one of the most powerful events that's ever taken place in our universe. And, you know, it's really kind of an embarrassment that they could barely see it. It's sort of, so one of my colleagues, Tony Tyson, was working at Bell Labs trying to build a gravity wave detector. And the president of Bell Labs came to him and said, you know, how are you doing? And so forth. And he was explaining it all to him. And he said, if a nuclear bomb went off next to the thing, would you detect it? Right? And gravity, the answer is no. Right? They're not very sensitive to seeing things in gravity waves. You detect the bomb going off because you'd be vaporized. Okay. So here's the other thing to draw your attention to. On this axis is the velocity, the orbital velocity. And you'll notice the orbital velocity peaks up here at more than half the speed of light. So we're talking about things that are 30 times the mass of the sun, orbiting each other at 30 times the speed of light. It turns out that they're orbiting many times a second. It's very impressive kind of time scale. And so that's the main thing that I want to say. This is the black hole separation. As they go in, the faster they orbit, the faster they radiate, the closer they get together fast. So at the end, it goes very fast. Okay, here's the thing that take from ornithologists, which is if you listen to bird chirps, you plot the magnitude, versus time and the frequencies you hear, right? So if a bird chirps, if it's a rising chirp, right, that's what you have here. The frequency is going up. Now, bats do echolocation with a falling chirp. So to the physics people in here and the engineering people here, why do they use a falling chirp? That's a homework problem. Okay. So this is a tool, and you'll hear this a number of times in some of the events. Okay. So here, imagine you could actually image these black holes. You will see the bending of space-time by the curvature of space-time by the heavy masses. If they're in a galaxy, which we know they were, then you would see the stars from behind them imaged like this. Now this is sort of more idealized. You'll see them come close together. You will notice there is a ring further out, which is the Einstein ring. And when it closes down, that's the last part to get done oscillating. There's a lot of interesting physics and so forth going on, but it's sort of, if you could watch this, you would actually see the evidence of what's happening. So let me go briefly through the history of detecting gravitational waves, because just like there was a lot of argument whether the gravitational waves and if they carried energy and so forth, that went on for 40 years. There was 60 years of efforts to try and detect gravitational waves. Most of those were failures, and there were some misleadings, and many people got discouraged, particularly if you could set off a nuclear weapon next to your detector and still not see the gravity waves, right? It's whatever. But there came an important event, which was we had very good indirect proof that gravity waves existed. And that came from the work of Holtz and Joe Taylor. They were studying a binary pulsar, which we believe to be magnetic neutron stars that are oscillating and putting out well-timed pulses. Since they're rotating they're very accurate clocks, you can measure the timing and measure the orbital parameters very precisely and measure how the orbital parameters change with time. And so they have done that over a number of years. This is the scale size, given the diameter of the sun here, and the scale size of what the pulsar was doing. And you see over here the prediction from general relativity of what the change in the shift in the periastron, the time of closest approach, should be over time due to the loss of energy from gravity waves. And so you'll see it's very nice, and there's a good place in here where you can, point, because remember they got the Nobel Prize in 1993. It disrupted their observational program. They didn't get back to doing data analysis for another year, and because the Nobel Prize does disrupt your life some, as you can ask the current year. Barry was supposed to come through and visit. We'll see if he does or not, and so forth. So, but since then, people continue to follow it. It follows exactly on this curve, right? And it's interesting because the two neutron stars are about 1.4 solar masses each, and they orbit each other at 7.75 hours, right? That's very impressive for thinking about two things orbiting each other at 8 hours, but we just had something where they're orbiting many times a second. So our scale of what's accepting is going on. And you're measuring a change of 76 thousandths of a second per year. That's what's going on. So the key issue here is that gave us confidence that general relativity was correctly predicting the amount of gravity waves that should come out. And it also gave us confidence that there existed binary neutron stars. And in fact, that was the primary science driver for LIGO, was to develop a detector that was capable of measuring the end stages of binary neutron stars, because we knew they were there, and we could make a prediction of roughly what the rate would be. We were pleasantly surprised by the fact that the number of really massive black holes was much bigger than anyone expected, or anyone reasonable had predicted ahead of time, right? Almost by 2 orders of magnitude. Okay. However, one of the first people to get really serious about detecting gravity waves was Joe Weber, and he was a very good experimentalist, and he had a very good sense. He was trained as an engineer, but he was very interested in the science and so forth. And so he went to a gravitation meeting in which there was a big argument about whether gravity waves were real or not. And at that point, people started to take them more seriously. He thought he should follow up, took sabbatical and went to Princeton, helped design and came up with a scheme. He thought of several different schemes. In the end, he developed what's known as Weber bars, which are resonant frequency antennas. And so here's a picture of Joe Weber in his lab with this big cylinder of aluminum, which is supported on a cable. You see the cable supporting it and the sensors that measure it. And so you have a standing wave, so the ends are fixed, and it bows up and down the middle, waves up and down the middle, and you measure the waving up and down. So that's the plan, right? So Yuan gave me this lovely picture that said, you know, the concubines don't sing, I think. I can't read Chinese. But the issue is they didn't really resonate, right? He chose a resonant frequency of 1660 hertz. That's 1660 hertz if I've done it right. Okay. And what you're wanting for is a gravity wave to come by and excite the bar at that frequency. That's the trick. So he began to claim he was seeing detections, but he's only looking at a very narrow bandwidth. It takes a tremendous amount of power of gravity waves coming, and he was claiming he was seeing it. He had in Maryland and in Argonne Laboratory in Illinois had 2 detectors, and he was doing timing between them. Okay. So, you know, if you're an opera singer, you can go swing through the note till you get the resonant frequency of the glass and break the glass. But here, the galaxy's just putting it out, whatever it is. And so it seemed unreasonable. Many people then rushed into the business of trying to build Weber-type bars, including Tony Tyson, and to make these detections, and all came out with a negative answer. And it wasn't until Hulse-Taylor binary that people got enthusiastic again and started thinking it's a worthwhile thing to do. But a thing that goes unknown, besides his claims for detections, he actually gave the first public lecture on laser physics, and he actually discussed with his graduate students and postdocs the idea of making a laser interferometer, but realized that it wasn't practical at the time, or didn't think it was practical at the time, and forgot about it. However, later, this idea is revised, and it's revised in a couple ways. First, the laser interferometer gravity wave detector was outlined by two Soviet scientists, 2 Russians, Gerstein and Postvoid, in 1962, and the idea was revived in 1966 by Vladimir Brzezinski, who's a well-known to some of us, you know, Soviet experimentalist, extremely good person, and so forth. And this becomes relevant in the story of LIGO a little bit later. But at the same time, Steve Weinberg was a professor at MIT and teaching the cosmology course and doing the things that was leading up to his book, Gravitational and Cosmology. That was the course notes. And he left because he and his wife were both offered a job at Harvard, and so a double job. And so the dean called upon, or the chair of the department, called upon Ray Weiss to teach the general relativity course. And Ray Weiss tried to teach this, and he couldn't understand what Weber was doing and how it worked, and he couldn't understand how you detect gravity waves. And so eventually he met with his students in seminar after the course, in a special seminar, and came up with a scheme, you know, in the seminar and discussions with the students, came up with a scheme of using the laser interferometer and put it out, published it in his quarterly progress report, which he had at the time a grant from the Air Force. This is just before the Mansfield Amendment, and proposed this is the kind of thing we're doing, and then decided that the best way to do that was to do these observations from space. And he and I think his name, Kip Thorne, ended up going to a meeting that I went to when NASA was looking for physicists to propose experiments for space, and he was proposing to do that. But he and Kip Thorne met the night before, spent all night discussing how great it would be to do this kind of stuff. And Kip Thorne had been to Moscow before and met the people and been excited about this idea and didn't know how to do it. And he said, yes, we'll partner MIT and Caltech, and we will push forward in gravity waves. We'll share information. We'll go back and forth. And he wanted to hire Brzezinski, but Brzezinski couldn't be hired. The Soviet Union would not let him leave. So Ray suggested that he hire Ron Drever. So Ron Drever was an extremely good experimentalist. He had a tremendous reputation. Neither one of them knew him personally, but he had done a lot of very impressive experiments before that and was starting to look at gravity waves in his own group. And so they made a hire, and that turned out to be important because it caused Caltech to move forward very quickly because Drever was making a lot of progress and Caltech was getting more money. They were making a lot of progress. Ray wanted to compete, so he ended up eventually asking NSF for money to do a study on how to do the right level of thing, which he had said in the report, how to make stuff on the proper physical scale. That became the baseline, what became LIGO. But it turned out that Ray Weiss and Drever had incredible fights all the time. And that turned out to be a serious problem and slowed things down for a while. And I don't know what would happen if Brzezinski had come, but we'll see. All right, so here's the history with a little slight red footnote. So in late 1979, the NSF gave limited funds to Caltech and more modest resources to MIT for the laser interferometry, so they were doing it. MIT had to switch because the Mansfield Amendment said no military money could go into basic research, so that they had to get new sources. And at that point, Caltech was getting ahead because they had more resources and more person dedicated full time. And so Ray responded by putting together a team that put in a proposal to NSF in October of '83. Its original, I was around, this original idea was going to cost $30 million. By the time the proposal went in, it was $100 million. You'll see at the bottom, it went off the bottom. So when I added that note, it came up to $620 million up to present time. So the price has scaled up, but this came and so forth. It came in various steps. In 1984, funding for a joint effort was approved, and construction started in 1992. And in 1994, Caltech was forced to make some adjustments. They hired, because because of the infighting and because of personalities, the LIGO was floundering fairly terribly. They hired Barry Verishin. He established a science team separate from the project team, and he also made it an evolutionary technical kind of a progress. And that became, he became first the PI of the whole project and then director of the project. So there were sort of two different hats. And he set the project up and led it to success, right? And so the question is, of all these people, who deserves the credit? The people who were the originators, the people who carried it out, the people who made the discovery? It's a tricky question, so that's the kind of stuff. So the initial operation of LIGO was from 2002 to 2010. You guys didn't hear anything from them, or very little from them. They made no discoveries, they just improved and did better, right? But they came back with an upgrade, and in this time, Tony Chan went to be head of math and physical sciences at NSF, and he got to sign the contract for the NSF side to Caltech, to the LIGO Corporation, which was Caltech and MIT, and they did an upgrade. The upgrade took 10 years, so this is during his term when he showed up. It took 5 years to do that, and then in late 2015, Advanced LIGO started to do its observations. So there's a long historical kind of evidence, but you see how the collaboration, how it took 40 years and how it took a lot of learning to figure out how to build it, even though there was a very careful design study done beforehand to actually learn how to build it and operate it, and then how to upgrade it. And they're still in the process of upgrading it. And if I have time, I'll talk briefly about that. Yes. Sure, of course. I put this in just because I knew you were going to show up.
I actually signed a contract with LIGO and Virgo.
Oh, between LIGO and Virgo. Sorry. All right, well, I'll fix it.
But the fun thing was, Advanced LIGO happened around 2007. And this is before they hear anything.
Right.
So you imagine, you ask for another 20 million to fund something.
Yes, no, I understand. Yes. No, LIGO was very, NSF was very farsighted and took a certain amount of gamble in this kind of a process. But it's turned out, as you will see, it meets the requirements of what I think an ideal requirements for a Nobel Prize. It's a great discovery. It confirms a great theory, but it's also a great discovery. But it also opens up a new branch of astronomical science. And there'll be a whole new generation of people doing it. Plus, there's additional science you're doing, additional fundamental science you're doing with this. So it's a big discovery that opens a big field, and that's one of the reasons that I think it's a well-deserved Nobel Prize. Right? Okay, so here's the pictures again of Livingston and Hanford and their location, 3,000 kilometers apart, 63,002. And
a laser beam is split and
here's
sent
the
down
concept,
a pair of
very
long
simple.
perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
Sounds really easy. It's a lot more complicated than that, and they show you very exaggerated how big the effect is. It's a tiny fraction of a wavelength. You'll see that the gravity wave stretched the 3-kilometer arms by an amount that was less than 1,000th of the size of a proton, and yet these are angstrom-length lights, 10 to the minus 8 kind of stuff. So it's a very big effect. It's also a lot more complicated, so you'll see there's a laser here. This laser is about a 100-watt laser. There's a mode cleaner and a lot of things to do to make it very pure and nice. There is a cavity in which the power builds up to it's about 6 kilowatts. And then in here, there are extra mirrors. It's not just the way it is. There's mirrors that bounce back and forth here. And this was one of the big fights between Ray Weiss and Ron Drever. Ray Weiss wanted to make a system of concave mirrors when you send the beam back and forth about 100 times in a complicated optics path and back out through a little hole, right? What Ron Drever did was say we should make it a Fabry-Perot, and they had a big fight about that because the Fabry-Perot is more difficult because now you're seeing on average more than 300 bounces, but some guys do 1,000 bounces and some guys only do 100 bounces. It's a very variable kind of a thing. And so in the end, you end up with nearly a megawatt in each arm, in the stored parts of the arm, and you're going to stretch that. And that, one of the things that Ray Weiss did was understand what physical scale you had to be on and what kind of things going on, what other kind of things you were needed in order to measure gravity waves in the range for the neutron stars and make it all work out. And come to realization that ultimately you're limited by the uncertainty principle, and therefore the masses of the mirrors and energy in the beam, the number of photons in the beam, were ultimate limitations on what goes on. So I have another little...
An interferometer, a laser beam, is split into two beams. Mirrors reflect the beams, so they meet again at the starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. We can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
So it turns out that the physics is relatively straightforward to think about. It's the engineering and the execution that are really the difficulties. Okay, so here is a simulation again. You see the two black holes. Below that in the color, you see the distortion of space, and you see arrows, which are the directions that test particles would go. And now we're watching the last half second of their lifetime. They're going to orbit several times. And the black holes will get radiating away gravitational wave energy in the form of disturbances in the space-time. This is sort of a cross-section of what's going on. You'll see the potentials are getting closer together. We'll slow it down in the last 200ths of a second. If you watch carefully, you will see there are two horizons. There's an apparent horizon and an event horizon in the black holes. The apparent horizon merges, and then the event horizons merge. And then you have an almost sphere that oscillates down to become very spherical. That's the ring down. So you have the chirp up, the merge, and then the ring down. Oops, I think. Okay, so here are the events. I showed you these before, but this is just to show you the new numerical relativity. That is, you do this on machines. You have to make templates, assuming what the masses are, what the spins are of the black holes and orbit parameters, and then try and fit the data and put it, and also the frequency response of the detector, and put them all together so you see these kinds of things. Okay, so when you have two detectors, and you measure the time delay between them, there's a circle on the sky from which they could have come from. There's certain directionality, this quadrupole directionality of these antennas. So you're able to reduce the location to the area that's shown there in the green and shaded by the probability, whatever it is, right? And so that is an issue, and I'll skip over a couple of slides to show you this. So what was happening next after this discovery? Well, there's a 2 there. Virgo, it was a detector. There's a Geo 100 and Virgo, which were built in Europe. They were being brought online. Geo 100 is only 600 meters long. Its sensitivity is lower, but Virgo is near 3 kilometers. That's what the video was from. It was in the upgrade phase. And so when LIGO saw that first event, it was actually still in its engineering commissioning, but the people who done it had gone home by 1 o'clock in the morning, and this event came in just before 2 o'clock in the morning at local time. and therefore they were able to detect it and declare that at the beginning of the run, even though they were anomaly in the mode. So they were very lucky. This incredibly beautiful event came when they just happened to be in quiet mode where they could receive it and detect it. And the problem for the team was, even though they have a set of people whose job it is to introduce fake events to keep everybody on their toes, this was an engineering run. Nobody thought any fake events were on. They thought this was a real event. And so word leaked out to some of us that they had discovered this interesting event, right? That's my sort of getting it. Okay, after the original discovery, the people in India got very excited and signed an agreement with LIGO to produce a corresponding one. And the people in Japan have been working on an underground superconducting detector, which should be ready at about sometime after 2020. And so both of those guys are post-2020. There are some other things that people are talking about, and we'll talk that there'll be other ways that we can detect it. Okay, so here's the issue. The original LIGO, when it turned on, was in this little red sphere. Its sensitivity allowed it to see these kind of events out to the size of that red sphere. They made these upgrades, and they improved the sensitivity by about more than a factor of 3, which increases the volume out to this yellow area, which is a factor of almost 27 in volume. Therefore, the event rate should go up by a factor of 27. And if they make the additional improvements, and I'll show you some pictures about what improvements they could make if we have time, or if you ask questions, then they should go out by another factor of 30 in terms of event rate. So, going from seeing a few events to where we should be seeing them routinely is within the purview of what funding and so forth exists now. So, right, and as you go out, you enclose more and more clusters of galaxies, and therefore do expect to have more events. And as you go out to the very large scale, you're starting to just integrate by volume. Okay, so that was great. And this is a cartoon that came out, and the next day an event came out. So this is really sort of interesting. These guys, they're gravity wave astronomers, you can tell because they have a telescope, but actually they're looking at computer screens, because that's LIGO. Everything is done by computer screens. And in fact, it's done by AI that looks for events and sends an email to the people on shift to please look, right? It's already an example of how things are advanced. Well, this is meant to be funny, that this guy in the background was pounding on the wall. But in fact, there was another event.
1.4
really was one day
billion
later.
years ago, two black holes performed a cosmic dance. They spun around one another, coming closer and closer together until finally they collided. This dance created ripples in the fabric of space and time, also known as gravitational waves. In December of 2015, those gravitational waves reached Earth and were detected by an instrument known as the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Scientists with LIGO announced the detection of the two black holes on June 15th.
Now, can you tell this is higher frequency or lower frequency?
This is only the second time that scientists have ever directly detected gravitational waves. The first detection, also made by LIGO, was announced earlier this year.
So if you listen carefully,
Currently,
the other one was higher.
all other
So
telescopes
these are lower
and
mass.
space observatories study the cosmos by collecting light or other particles. But the black holes detected by LIGO are not expected to radiate light. So by looking for gravitational waves, LIGO is illuminating otherwise.
So this is an ad. Okay, so this is very different looking. It goes on for a whole second, okay? Not a half second, this goes on around for a whole second. And so you have a lot more of the sort of ordinary orbits slowly losing energy until you get into the final stage where it does. This ends up making a 21 solar mass black hole out of a 7.5 and a 14. So the chirp mass, the frequency you hear, is much higher because the chirp mass is lower, right? So it's reciprocal of chirp mass. But it has the same sort of behavior. You're going to get up to near the speed of light, half the speed of light, just as you cross the thing together. This one was best fitted by having a spin of about 0.2, which is an interesting question because where these black holes come from, will they be maximally spinning or whatever. There's a lot of questions about what's the progenitors, what kind of things are they. Okay, and so if you look, there was a candidate event that didn't meet the threshold. So there was the first event, which was less than half a second. There was a candidate detection, and then there was the day after Christmas event, which is the one that I just showed you about. So these, I'll skip on because it takes a while. That I wanted to show you, nope, it's the next one. How do we know what we saw? Well, you can just do the simulations of what a binary star neutron in spiral should look like, and you see it's very high frequency, and it goes on for quite a while. And you look at the best fit for that first event, you see the frequencies are very different. It means the mass, these masses are much lower than those masses in terms of what's going on. So that's one of the ways we know. So what happened time-wise? Well, there was an event before, this is LIGO's first observing run. It was supposed to be the engineering run here, but it's the first run. Right? They saw an event in September, an event in October, possibly, and then an event in December. So the very first run they turned on, they see 3 potential events, 2 events that meet the criteria. So you can predict how much you should see. Then they turned off to do upgrades. Okay? And there were a number of upgrades they did. And what you'll see is that Livingston made all the upgrades that they were planning to do, and Hanford had to take one of them back down, which was the increase in laser power. But here are the events that they saw and the places on the sky where they should come from. So they come from random places in the sky. This is consistent with the best fits that these are coming from cosmological distances. Okay, and they pointed out that had Virgo been online, the localization would be much better because you would have crossing circles on the sky, and the inner overlap of the crossing circles will be around. Okay, but in September, just 2 weeks before the Nobel announcement, there was a new data event released. You can see the waveform from Hanford, from Livingston, and from Virgo, which is barely showing up. You can see the chirps, and now you see the signal to noise in Livingston is very good. The signal to noise at Hanford is not nearly as good. You can see that in the raw data here too, how much better this is. And from Virgo, it's not quite as good. However, having 3 detectors does allow you to localize the event significantly better. So this is a picture of the Virgo Observatory, and it's in farmland. They just built it right in the farmland. It's very near Pisa, and it looks like this. And you'll actually see in one of the movies they mislabel and use one of it. But it's fine. So Virgo provide the improved localization. So the yellow curve on here, whoops, push the wrong button. The yellow curve on here shows you what you get from LIGO, and then the green shows you what you get when you do the very quick solution. Because this is being done with AI, it does a very quick solution, and it makes an estimate of the best location and sends that out in a telegram to astronomical community to look. And then you go back through and do your numerical relativity and solve it better. And there's a phase shift and adjustment that's done to make the best fit. And it becomes that purple one. So you actually told the astronomers to look a little bit in the wrong place. But that's, this is getting the bugs out. But this is telling you how much you're depending on the AI to first get you the event and then to actually fit to that event and refine that location better, right? So here's the event, the 3 events you saw before, plus the 4th event that got added on. So they released this data as kind of welcoming LIGO into operations, right? That LIGO is finally working. Although you'll see, if I have a chance, LIGO is a little bit behind, Virgo is a little bit behind LIGO in terms of its operations. Okay, so here's a plot of what we know about black holes of known mass. I'll show you another in a minute. But one of the things we're starting to see is that LIGO plus Virgo, but mostly LIGO, are seeing a number of black holes of a larger size than we've been seeing from our own galaxy and our own local cloud. And that's because there's a selection effect. It's easier to see the more powerful ones from further distances, but also there's more of them than we expected, but we're going to work on that, see what happens. Here's pretty pictures. Here's the events. As you'll notice, everything is over in less than 2 seconds and all this. These events don't last very long. It's kind of stuff. But you're looking out to fairly long distances. Here's sort of an interesting plot. The neutron star frequencies are going to fall in this range. This is what LIGO was optimized for. This is the Livingston, the Louisiana detector. And you see its noise floor. There's uncertainty principle in this direction, or uncertainty principle and seismic noise in this direction. And here is the Hanford one. They weren't able to increase the laser power, therefore they didn't able to increase the low sensitivity, low frequency sensitivity the way Livingston was able to. And hopefully in the next shutdown they will get an improvement. But one of the things you will see is there's lots of resonances still. If you look, and I'll show you in the next picture, we'll just go to it now. Here's the Virgo, which is even worse, right? You see how many lines there are in Virgo. These are just mechanical resonances and feedback resonances in the system that have to be treated. So when the data analysis goes on, these things are filtered out, the thing is reconstructed and put back together, and there's kind of an issue there. But part of what you have to do is you learn about it, and you have shutdowns, you learn how to put some of these features out. So that's the issue that's going on. So you can see how Livingston has gotten ahead of the other two, but generally LIGO is doing very well, although ultimately it wants to get down to this kind of sensitivity. That will get them out to the range in which they'll be making detections every month. Okay, so there's a whole set of things that we're doing, because I want to get on to the next event after the Nobel Prize. There is a whole set of things you can be looking for gravity waves. And what we've been hearing about is the ground-based laser interferometers, where you will see neutron star mergers and black hole mergers. We'll talk about the neutron star mergers. There has been proposals in for quite some time for a laser interferometer in space array, dating all the way back to that early time when Ray Weiss was trying to convince NASA that they should be thinking about doing this way before it was time, but it's time. But there are proposals now and serious programs in and discussions of launching by like 2030 satellites that will be making these measurements in this range. And they're really looking for the supermassive black hole mergers from when galaxies emerge. In the cores of galaxies, there are supermassive black holes. When the galaxies merge, the black holes will eventually get together and merge in. And you can also see them by doing the pulsar time rate. Take these neutron stars with these very, very regular clocks and just measure the time arrivals of these pulses and look to see a gravity wave pass between you and the pulsar and see how it changes the time arrival. And you can also look for primordial gravity waves. And 2 years ago, almost, we had a report from the BICEP-2 experiment that they sent a pattern of polarization of the sky, which would be the pattern you would see from primordial gravity waves from the beginning of the universe, from inflation. And it also turns out to be a pattern you see from magnetic fields, and what they saw could be explained by the magnetic fields of our own galaxy and whatever it is. So they're doing it. And one of the people there just sent me a book to review about the missed Nobel Prize that they had. But anyway, I have to read it and see what's going on, but it's in my computer. So this is the science that we're after in looking for gravity waves, but there's a lot more science to it. Right? So you say, well, where are the sources of gravity waves? Well, from the Big Bang, from the early part of the universe, there's a huge bandwidth, a huge frequency range over which you expect gravity waves. And some of them come from the actual making of space-time, and some come from phase transitions and other phenomena that happen as the universe is expanding and going through its cycles. And then there's the supermassive black holes and the compact binary objects that are merging and in spirals and so forth. And so these are the kind of things that people are interested in looking for. And here's one of the things that became immediately apparent. We didn't realize there would be a significant population of binary 30 solar mass black holes. If you do that and you put LISA, in this case it was E-LISA, but LISA is the sort of new version. If you look, they will appear for roughly 10 years in the bandwidth of this laser interferometer in space. And as you orbit around the sun, you can track and get the angle of position very accurately within a degree, and you can make a prediction to within a minute of when it's going to coalesce. So you can tell people where to be looking and when to be looking, when to have your gravity wave interferometer on, when to have your telescopes pointing at the place. And then they come into the advanced LIGO band and the Virgo band, and they show up and do the collapse, right? So this is one of the things that is now driving the design of the laser interferometer, is to be able to do this kind of thing. Whereas before, we wouldn't have bet that there were that many 30 solar mass black hole pairs to deal with. And so there's a whole series of things. I want to skip on. And there are astrophysical implications about what's going on. There are tests of general relativity. You can look now, because you're seeing the stuff in the strong field limit, you can look as it comes in the final orbits, and then you look for the ring down. You can do tests of the various properties. There is a formalism for extending general relativity or expanding general relativity and looking to see what compares to the parameters you expect from general relativity. So far, everything is fitting right exactly on general relativity. So that's an interesting aspect. It's going to be a lot more data coming in the future. Okay, so we have the first detection of gravitational waves. We have the observations of black hole binary, the formation of a black hole, and the most luminous stuff. So these were new window on the universe. This is the stuff that was existing right up to the Nobel Prize. But then there's more, right? But we have the 2 neutron stars that were announced shortly afterwards.
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery. On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma-ray burst was detected by NASA's orbiting Fermi Gamma-Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma-ray burst was unusually weak. Gamma-ray bursts are usually so strong that researchers assume that the gamma rays emerge from 2 back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma-ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma-ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
So some of that's controversial, at least to me.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of 2 neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, chirp, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with the target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron-star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
Okay, well, here's a simulation that was done of two neutron stars before the event was discovered, just to show you. It was our idea for some time that two neutron stars emerging lead to the short gamma ray bursts. They only last less than a second, and so it has to be something whose light travel time is less than a second. You know, it's small in order to be able to do that. So we'll see. And there's issues. It's a lot messier to think about a neutron star than it is to think about a black hole. You know, I prefer electrons on electrons because they're really unique and whatever. But black holes are pretty close to simple objects. But a neutron star is really messy. Neutron stars have magnetic fields. They have neutron matter, but they have some crystals, some other material. They have a lot of kinetic energy. You have to merge them together, organize the magnetic fields. There's a lot of things you have to do in order to have a merger happen. So it's not surprising there's light, but it's also not surprising it's going to be a lot more complicated. And it is sort of surprising that I gave you the hint of where you can find, 5 Earth's masses of gold if you just go and look for it. Right? It's a simple tip, right? So this is a much richer field in terms of what's going on. The papers, instead of being 4 or 5 papers, there were 30 papers that were released with this on the day that it was announced. So here's a binary neutron star. And you're going to get to see the computer gets to make art too. But you can see it's not nearly as simple as two black holes merging. Because there's an outer atmosphere, and even though it's only a teeny fraction of the total mass, it has a lot of complicated things going on in it. And there's an interesting question of why it was the 1.74 seconds from the merger till the gamma ray burst, right? And because we would think that it's somewhere on the order of 0.04 to 0.4 of a second before you form the black hole, unless there's some extra factors involved. So I have another sort of more detailed video to show you. It's got music, so you'll be more impressed by how pretty it is. But you can see the black holes, they just had an event horizon. They didn't have this little atmospheric halo coming out and getting, you get to see it 3 times. So you get an interesting set of accretion disks and things that are feeding around the spinning black hole. We don't know how it all goes. Our model is something complicated. You have an outer spell, you have jets, you have all kinds of halos and things that are going on. And because you're sending your beams through this material, you get afterglow. And it shows up in the X-rays, it shows up in the infrared, and eventually in the radio. And now we have an even larger plot of what's in the stellar graveyard, including the last event, which was a low mass, relatively low mass neutron star and a relatively high mass neutron star merging to what may be a very high mass neutron star or maybe a black hole. Those are the things that we have to determine and figure out whether it's really happening. And so it's the beginning of studying what happens at the endpoints of stars and understanding how that develops. And we're building up a catalog from various sources, but now we have a new source of catalog. And this was just where it's from. The important thing was, how did Swope find it? They were told roughly where it was. As you saw, there was only 50 galaxies in there because it was in this small region labeled HLV. But there's an additional thing you have from the gravity rays, which it tells you the expected distance. So you're seeing kind of a conical shaped region in which to look. That's why there's only 50 galaxies in that region. They couldn't start observing until the sun set. So that's why it took them 11 hours. They could have started looking earlier, but in fact, it wasn't dark in Chile yet, and so forth. So they went in and they searched in these regions, and they managed, either by intuition or by luck or whatever it is, to zero in on one of the 50 galaxies that gave them a lot of information, and that got followed up by these other devices, these other things, and then many observations after that. And so we have a lot of data, and we have data of the signal versus wavelength and the signal versus time. There's a lot of information here, but it's also a much more complicated system. So, we know this is not a particularly interesting galaxy. It's kind of a dwarf metal poor galaxy, but somehow it had this interesting event in it. And here's what I was pointing out again about the timing. Here's the end of the chirp, and here's the time till you see the gamma ray burst. And it's actually, even though here it's just 1.74 seconds, it's still, that's a long time on the scale of these events. And so what's going on during that time, right? And so that asks the question, what's the fate? Do they make a stable neutron star? Do they make a black hole? Did it take a while? Are they supported by its rotation and eventually it will collapse? What's going on? Those are kind of questions that people, so there's a whole new field that people kind of have to study and understand. And we expect there'll be more of these kind of events in the future, so we'll see how that goes, right? And so this is the end. There's, you get pretty pictures, you get art, as well as good music and so forth. And so I stop at this point so you can ask questions.
There are mechanisms to damp the vibration of the gravitational waves. If not, then would the universe be filled with gravitational waves from all these, merging events from the beginning of the...
Yeah, so the question about ramping the gravitational waves, the same question is how easy it is to detect them, right? How we had to spend $600 million to be able to barely detect this. And
what I'm asking is, what's the general relativity mechanism? Once you have these gravitational waves, okay, that keep on traveling in the universe, do they ever get disappeared eventually?
Right. So what happens is, just like any other form of energy, if it's going out spherically, its energy is falling down as 1 over the distance. The energy density is falling down as 1 over the distance squared. So effectively, it gets lower and lower in terms of its strain and its effect until at very great distance it's very small, but it never drops to zero. It's just like gravity doesn't drop to zero, unless there's some shielding. Right. So what we expect is from the early universe, there are gravity waves floating around from events in the early universe, and they're just propagating around, and they're just diluting by the expansion of the universe. They're still there. They're still residual. There is very little absorption of them, very little other things. They're just there. That's why, in principle, it's possible for us to be looking for them. And for the supermassive black holes that are merging in galaxies, the detector, the laser interferometer in space should be able to detect them across the whole visible universe as far as light could have traveled during that time period, or gravity waves could have traveled. So one of the things we know is the gravity waves are traveling too close to the speed of light. Just the fact that the two signals appeared at roughly the same time is an indicator. The fact that you can see the timing across between the two detectors tell you the gravity waves are traveling close to the speed of light.
On your map of various observatory, China is missing. Is there any plan that China is contemplating?
Okay, so I have to be careful about what I have to say. So there is an effort by some Australians and by some of the universities in China to make a sort of ground-based laser interferometer system. But there's very much interest by the Chinese Academy of Sciences in a space-based gravitational wave mission, and also in Guangzhou. So there is a three-way tension as to which way the program in China should go. But at the present time, it would seem the Chinese Academy of Sciences has a strong hand in terms of finances and other things. And so, I would think China could do all three, but in practice, probably one group will win out. But we'll see what happens. Andy might want to comment on this.
No comment.
Right. So I wanted to be careful, but so this is an issue. Is that there's a lot of really exciting and interesting science. It's clear to me that gravity wave physics is going to be an exciting field for the next 20 years. Building scientific capability and building up observational data. Starting 20 years from now, it'll mostly be doing observations and it become a more routine astronomical kind of thing. But it's still going to be an interesting field. But it'll transition from being a field where you're pioneering to a field where you're doing science on a regular basis. And so it's a very interesting field, and a field which it makes sense, the different kind of programs. I tried to convince a couple people in the Chinese Academy of Sciences they wanted to have a space-based program and a ground-based one so they could have some results, because it'll be a while before, something gets in orbit, but it's clear that they were very interested in the space-based program.
Professor, is the gravitational wave has anything to do with the gravitron?
Okay, so the question is, does the gravitational wave have anything to do with the graviton? And the answer is, for what we're talking about, you can treat it all classically in a certain sense. But if you want to think ultimately that things are quantum-based, then you can ask, what is a wave made out of? And your argument would be, just like a wave of light is made of photons, that a gravity wave will be made of gravitons, and so forth. So the graviton is the fundamental quanta of gravitational force, but it's also the carrier of the wave. Is that okay, Andy, or you want to give a different version?
No, I think that's fine. So the gravitational waves are made of gravitons, but to see the particle-like nature of gravitational waves is beyond our capability at the moment.
Right. So the hope that people had was the hope that we could see the gravitational waves that came from the beginning of the universe, of which then we think they're created directly by quantum processes, and that you would have an example to see the graviton in action more directly. So the excitement of the BICEP announcement and everything was both it give you an energy scale, but it also would give you the opportunity to see some quantum mechanical effects of gravity from the early universe. Here, everything we're talking about so far can be explained very well by classical general relativity without recourse to quantum mechanics. So we do think underneath that there's a quantum mechanics, but it's not necessary to use it.
Thank you for being here and for this delightful lecture. I'm wondering if a gravitational wave doesn't have an effect on the light itself used in the laser, because we know that light follows a different path when a mass is there. So I don't know if we can neglect that or.
Yes. So the answer is just the way it stretches space, it stretches the wavelength of the lights inside the interferometer. So if you thought about it as a static way, you would think, well, I stretched it, but the number of wavelengths stayed the same, right? I shouldn't see a change in the time. But the speed of light always remains constant. So the travel time depends on the matching of the two waves. So even though you might have the same number of standing waves. So the gravity wave does stretch the light, and that's because light happens to be conformal with space-time. So when the universe expands, it stretches light. When gravity waves come through, it also stretches the light. But in fact, you have to think about the light ray going back and forth, right? You can think of it as a standing wave, but if you look at the timing of what it takes, these guys that were in phase because there was equal length and equal distance, when the length got stretched and the wavelength got stretched, their speeds still stay the same, so that they get out of phase. When they get back, when they're going in the same direction, they're stretched the same length, and they end up being out of phase. And so it's more subtle than it looks. I give you the simple explanation because this is a sort of a colloquium level, but in fact, if you just do it in terms of light, if you do it the way Ray Weiss did it, just send the pulse back and forth, then it's easy to see that the gravity wave stretches it. The speed of light is independent of the situation of the observer or the transmitter. You will see that it takes longer in the arm that got stretched than the arm that got compressed. And so there's a phase delay between the two. And but yes, the light does get affected, and it gets affected, right? Same way it gets affected when light leaves the surface of a neutron star. It has a gravitational redshift, right? Because it's coming out of gravitational potential. It's affected a similar sort of way.
When this gravitational wave is traveling through the universe and it passes matter, does it scatter off the matter? Can we use it to probe what's between here and the source?
Yeah, so the answer to that is interesting, and that is scattering off of matter is you can think of it in that way, but it's probably easier to think about gravitational lensing of the gravitational wave. So imagine that there is the binary black holes or whatever is getting ready to merge, and there is between you and that, there is a supermassive cluster with a really massive galaxy in the center. You would expect gravitational lensing of the gravity wave coming, and it would take this spherical wavefront and distort it, and it can distort it sufficiently that you would see that wavefront twice, right? And you can ask yourself, what's the typical kind of time scale? And it could be years. There could be a displacement of years, or it could be minutes, or it depends on the mass of the object that's missing. If it's a 30 solar mass black hole, it's fractions of a second. It's so the time delay between the kind of things depends on that way. So you could potentially do that if your gravity wave detectors are sufficiently sensitive. You could have events, right, in which you have gravitational lensing. Now, you can kind of make an order of magnitude estimate of what the cross-section is for strong lensing. That's the case we're talking about, is when you actually see two different the image twice, and it's roughly a 10 to the minus 3 kind of number. And so if you had 1,000 events, you would expect to see at least one strongly lensed. There are some more, if these are coming over, depends on what distances they're coming over. So, but you will see distortions of the wavefront. You will see other kinds of phenomena. But the question is whether, the signal to noise here, it may be 100 or 50 or whatever, depending on how you count it, but the signal to noise on one local part of the waveform isn't so high, right? That's the problem. That's why it's so embarrassing that it's 50 times brighter than all the stars and you barely can see it, right? It means it's not an easy tool to use. One of the things that's been the mark of the last century in physics is how we've learned to use light interacting with matter extremely well to do all kinds of very precise measurements. It's going to be a lot harder to use other, particles or waves to be probing things. Now, it's still a big breakthrough because we now have gravity waves. We're now seeing parts of the universe we've never seen. We're getting a different inventory, what we call the multi-messenger, that is seeing it in gravity waves, seeing it in photons. In principle, you should have seen it in neutrinos, right? But in fact, it wasn't seen in neutrinos, so you didn't hear about that. But if there was a relativistic jet and it was proton-loaded jet, you would expect some of those particles to make heavy particles and some of them to decay into a beam of neutrinos. There would have been other things you might see. You'll learn much more when you see many different messengers coming, provided you can measure them and see them. But it's already very difficult for us to use neutrinos as a probe of things. You see people X-raying things, but you don't see people using neutrino, fluorescence or something like that. It's just, we know how to use light because the light interaction with matter is extremely high, right? Now, maybe there's some other substance, dark matter or something else that works as a neutrino or something, but probably not. And the question is, are there any other kind of things we could use as probes? But if I think about what am I doing for my research, most of the tools we use are trying to make better detectors of phonons or couplings of phonons to matter detectors in order to understand the universe better.
Thank you, Professor. At last, you asked us several questions, but I really want to know your ideas. The stars or the black holes merge and become one. So, what it is? How do you think about it? Is the when they emerge and when they emerge, I don't know how to describe that. Maybe it's not Earth, it's something else. How do you think about it?
So I'm not sure what the question is. Can somebody give me a hint?
Because two stars emerge to become one, then the creativity is spring out, right? But
Right.
when they emerged, what exists actually?
Okay, so the two neutron stars or the two black holes? I mean, the black holes, I think we have a good understanding. The two neutron stars merging, I don't think we have nearly as strong a theoretical understanding of what it is. And in fact, we hope we'll observe many more so we can begin to learn about what's going on. And so I would have thought when these two neutron stars merged, eventually it's energetically favorable for them to collapse into a black hole. They're a very unstable situation. And then the question is, is there a rotation and is their equation of state sufficiently stiff to keep them from collapsing? But one of them is on the scale of 1.1 solar mass and the other one is about 1.7 or something. It's over 2 solar masses, right? And that's getting up to the point where the Pauli exclusion force pressure of the neutron stars should yield to gravity, right? And so the question is there something else going on? Is there strong forces or what's happening? And did they lose enough mass? They couldn't have lost that much mass, but did they lose enough mass to keep them from getting over the critical limit, right? Before they finally emerge. So I don't know. This is a new event. I don't know. There's a lot of stuff that I had prejudices about. Now I have to review and think about more carefully and try and understand. And so I'm not sure what's happening there. It's kind of interesting and exciting. I have trouble believing that they make the gold on the Earth, right? And I explained it to you, right? Most of the things there was 6 things that were listed that form the elements. Most of those happen sort of uniformly or relatively uniformly throughout the universe or throughout the galaxy, like the cosmic rays hitting things. Cosmic rays go around the galaxies. The neutron star mergers are relatively small. And the neutron star mergers then have to blow these heavier elements out and spread them through the environment and then mix them with the material from other stars so they can collapse to form the planets and so forth. So how big a region do you think a neutron star merger can explode, right? Well, the galaxy is about 10 kiloparsecs thick, but it's about 100 kiloparsecs wide. So its ratio of area to thickness, right, is roughly 10 to the 4th. So if every neutron star could fill up a volume like that, you need at least 100,000 such mergers. I would guess closer to 1 million such neutron star mergers to uniformly populate the galaxy with this material. That's a lot of these neutron star mergers. It's not impossible. That's within a reasonable amount of how many neutron star mergers there could have been, but that's a lot. And we want to have the one in our neighborhood having taken place over 5 billion years ago, which is also possible, but it's trickier. So, there's a lot more to digest for the neutron star mergers than there is from the black hole mergers. The question about the black holes is where do they come from, right? And how do we test general relativity? For the neutron stars, where do they come from? How quickly were they there? What did they do? How do they throw out the material? How is that processed through and what goes on? So there's a lot of interesting questions here. And I had prejudices and now I have to learn more and figure out what's really going on. And so it's not impossible. It just seemed to me hard that we had 1 million of those mergers, right? But, if you do the numbers, that's how many per year in the galaxy, right? Well, if there's one every 100 years, that's enough, right?
Thank you. Since the gravitational waves travels in a speed close to a light, so as for the neutron stars, we notice that there is a delay between we detect the gravitational waves and we observe the electromagnetic waves such as the gamma rays. So why there is such a delay?
Okay, so that's a very interesting question, and I'm not sure why that is. So you have to ask, where would the light that we see come from? In this case, the light was first seen in gamma rays, right? So the gamma ray bursts. So by gamma rays, maybe relatively low energy gamma rays, but still in the MeV and somewhat higher range, up to 100 MeV, but mostly around the MeV and the kilo electron volts. And we think, historically, we've thought these come from relativistic jets that beam out, that as you form a black hole, you have to get rid of some angular momentum and so forth, and the magnetic field gets organized, and so you get this collimated place where you get a jet coming out. And then this jet is taking part of the material coming in and sending it out in shock waves and accelerating electrons, and those electrons are being accelerated, but they're also in a field of photons, and they Compton scattering, they boost them up to high energy. So there's a huge number of physical steps going on in there that predicts that you should have this relatively fold forward, because these beams are coming out probably with a gamma factor on the scale of 10 or 30, something like that. And so you get the beam folded forward by the gamma factor, and you get the energy boosted by the gamma factor, and so you get a gamma squared from the solid angle and a gamma from the, so you get a gamma cube kind of thing. So that's what you think the answer is. But the other possibility is that you had this tremendous thermonuclear explosion, and you produce a really hot plasma when you burnt up and made these heavy transuranic elements, or lanthanide series elements, and they let out a burst of gamma rays, and then they are slowly cooling down and are letting out X-rays and so on over time. There are different models that people have, and there are arguments. You saw in that thing where they're saying, we usually think there's these two tight back-to-back beams, right? But there are people who wrote papers at the time this came out that no, these beams are more broad and more diffuse, right? So because you can ask your question, the very first neutron stars that we should see, should the orbit and everything line up so the beam was pointing at us? And my conclusion was no. We're seeing the beam off axis, therefore its signal level should be low. And the signal level is lower than a typical short gamma ray burst by about a factor of 1,000. But you can explain that by being off axis by about 20 degrees with a regular beam, or you can say it's a much broader beam and it's going through more diffuse. And so the community has an argument about what's really going on and what's happening. But if you didn't form the black hole, then forming the jets is harder, and you can still get jets, but they would be the broader beam jets. And so we don't know what the answer is. This is, there's going to be a lot of papers and a lot of studies and speculations, and then there will be hopefully some more events, and we'll see this. This is exciting thing. Some of my colleagues and I have been doing experiments for almost 5 years, trying to catch the early photons from short gamma ray bursts to try and get some information, right? There's almost no such events that's seen in the optical and the infrared and so forth, which would tell you a lot about what's going on. We've always assumed, but never had proof before this, that short gamma ray bursts are coalescing neutron stars. This is evidence, except is this a typical one or is this a very unusual one? And why is the first event we saw unusual, right? That's, so you don't know that until you get a couple more events, and then you start to understand.
Okay, I think sadly our time for questions is up, although I'm sure that George would be happy to entertain your questions over coffee after today's lecture. So let's take this opportunity to thank George once again.